Modern commerce relies on a relentless global network of continuous physical movement. Millions of tons of cargo must cross oceans and continents every single day to keep shelves stocked and production lines moving. For decades, managing this massive flow of goods relied on a strictly retrospective baseline. Supply chain managers looked at historical sales data, observed what happened last quarter, and used human intuition to guess what might happen next. Because human intuition cannot accurately predict market volatility, companies are forced into a reactive posture. To protect themselves against unexpected demand spikes or supplier delays, they build physical buffers. They stockpile excess inventory, known as safety stock. Storing surplus material creates an immense financial burden. That safety stock represents millions of dollars of working capital frozen in place, sitting idle in warehouses rather than being deployed for growth or innovation. In critical sectors like healthcare, the financial damage is extreme. Hospitals must navigate dense shelves of medical supplies, and managing that physical inventory can account for up to 50% of a hospital's entire operating cost. When a disruption occurs in these traditional linear supply chains, a delayed cargo ship, a sudden parts shortage, the system breaks down. Companies panic order, leading to cascading inventory bloat, desperate emergency shipping fees, and widespread waste. A static, intuition-based supply chain is a fragile financial liability. To survive modern market fluctuations, algorithmic integration has become a mathematical necessity. The solution lies in shifting from human intuition to algorithmic intelligence, using data to dictate the physical movement of goods through every node of the network. Most organizations collect a massive volume of unstructured big data, weather patterns, social media trends, supplier lead times. Yet, this influx of information often creates paralysis because companies lack the architecture to process it. Without the proper computational framework, big data creates a bottleneck. It overwhelms human analysts, obscuring critical insights behind millions of unorganized data points. This hierarchical diagram illustrates the required framework for mastering big data in supply chain management. It breaks down into 3 necessary tiers of computation. The foundational layer is descriptive analytics. This tier organizes raw, historical data. It tracks key performance indicators to answer what has already happened, like order fulfillment rates and delivery times, creating a clean baseline. Once the baseline is clean, the system moves up. Predictive analytics takes that structured data and forecasts what will happen next. Finally, prescriptive analytics operates at the top, recommending the exact algorithmic actions a company should take. Following this hierarchical progression allows organizations to convert an overwhelming data bottleneck into a proactive strategic engine. The predictive tier serves as the critical bridge. It takes the organized history of a company and mathematically projects it forward, laying the groundwork for autonomous logistics. The core computational engine driving this tier is demand forecasting. This infographic details the multi-step methodology required to build an accurate demand forecasting model. Step 1 is comprehensive data collection. The model ingests historical sales records, current market trends, and external variables like weather indices. Step 2 requires methodological diversity. Analysts deploy time series tracking paired with complex causal models. Step 3 ensures an iterative process. Algorithms constantly adapt to new market feedback, refining calculations to maintain accuracy. Step 4 is the integration of technology. Machine learning hunts for hidden patterns human analysts cannot physically spot. Finally, Step 5 delivers strategic decision-making. The model provides detailed foresight that dictates exactly how a company aligns its resources. To execute this, machine learning replaces single-number forecasts with probability distributions. These map hundreds of variables at once. Instead of a rigid guess, the algorithm models both upside potentials and downside risks simultaneously, adapting as new variables hit the stream. Predictive mechanics do not blindly guess the future. They mathematically map all probable futures, ensuring the supply chain is never caught off guard by a sudden shift in the market. Applying these probability distributions to the physical world rewrites how warehouses operate. Instead of relying on a massive, static safety stock to buffer against the unknown, a company can deploy dynamic, algorithm-driven replenishment. The supply chain orders exactly what it needs, exactly when it needs it. Tightly aligning procurement with predictive demand actively prevents overstocking. Products flow through the facility without sitting idle, virtually eliminating the risk of product obsolescence. By utilizing machine learning to process historical sales and real-time market trends, Amazon reduced its inventory backlogs by 20 to 30%. Between 2019 and 2023, their inventory carrying costs dropped by an average of 22%. This exact predictive approach also prevents life-threatening stockouts in highly sensitive industries. Pfizer adopted Predictive Analytics to track and route its medical supply chain. The result was a 20% reduction in stockouts and a 15% drop in delivery delays, ensuring critical medications remained available without bloated storage costs. McKinsey calculates that by integrating these advanced planning algorithms, companies can reduce their overall required inventory by up to 75%. Advanced predictive analytics decouple a company's operational security from the crushing financial weight of massive physical safety stock. Once the predictive engine is running, an organization can move to the final tier of the hierarchy, prescriptive analytics. Prescriptive analytics moves into execution, using optimization algorithms to autonomously recommend specific actions, like identifying the optimal shipping route based on real-time risks. By sharing this algorithmic data with suppliers, external partners automatically adjust their production based on the central forecast. This mutual visibility eliminates the bullwhip effect, the supply chain flaw where a tiny shift in retail demand causes massive overproduction at the manufacturing level. When suppliers operate on the exact same prescriptive data as the buyer, it prevents last-minute emergency shipments, drives supplier reliability, and drastically cuts logistics expenses. The prescriptive loop even optimizes pricing. Algorithms dynamically adjust costs based on real-time stock levels, current demand, and the capacity to replenish the warehouse. Prescriptive analytics upgrades the entire supply chain. It evolves from a reactive physical pipeline into a proactive, self-optimizing digital ecosystem. The absolute frontier of this prescriptive optimization occurs when algorithmic confidence outpaces human purchasing decisions entirely. This enables the radical concept of predictive shipping, the ultimate endpoint of the zero-stock paradigm. In predictive shipping, physical products are dispatched toward a geographic region before a customer has even finalized an order. The algorithm mathematically anticipates the purchase. When the customer finally clicks buy, the system instantly matches their order to a shipment already physically in transit. The system utilizes extreme agility, automatically rerouting that in-flight shipment to the precise final destination via mobile network updates. This level of advanced prescriptive precision turns the traditional fulfillment timeline upside down. It eradicates standard delivery lags, turning days of waiting into hours. In a volatile global market, survival favors the fastest. Companies employing full-stack analytics outpace their rivals by operating with unmatched agility, achieving optimized pricing, and total logistical reliability. By ascending the analytics hierarchy, an organization strips away the wasted capital of safety stock and the inherent delays of reactive planning. The supply chain ceases to be a vulnerable operational cost center. It becomes an organization's primary competitive advantage.